Welcome students. Today we are going to take up a new topic, semiconductors. Okay. Now this is the final topic in your class 12 syllabus. Now basically when you talk about matter, matter has three forms: solids, liquids and gases. Now, how do you differentiate between them? So matter basically consists of atoms. So you have these are all atoms. Alright. So this atom to atom there must be some distance. That is called interatomic distance. Interatomic distances. Alright. So for solids it is very less. It is very less for solids. It is little more. It is much more. So here they are kind of packed. Okay. So basically when you talk about matter, this is the classification, general classification. Okay. So when you take a sample, the sample can have numerous atoms. Now here when you talk about solids, so suppose these atoms, when you talk about solids, solids can again be classified into crystalline and amorphous. So in crystalline you have a definite pattern of arrangement of these atoms. There is a pattern. Okay, you take a sample, either the atoms are arranged like this, or they are arranged like this, or they are arranged like this. There is a pattern. So that type of arrangement is crystalline. In amorphous there is no such definite pattern. So crystalline will have a particular geometrical shapes. You can expect a pattern over here, but amorphous you cannot expect that. So crystalline, your gold, silver, all these things come under this category. Amorphous means your rubber, plastic, they come under amorphous solids. So but we have to study these semiconductors. Okay, so what we are trying to, why we are studying this, when I will explain what are semiconductors, you will possibly try to understand what is a crystalline, why we are studying crystalline structure and all these things. Okay. Now see, you have a term called isolated atom. Okay, isolated atom means there is an atom which is totally nearby, there is no other atom. It's a single atom. It is a single atom. So this is atom, so it will have a nucleus. Around nucleus the electrons will be rotating. Okay, so this is the outermost layer of the atom. All these are what? These are all orbits. Alright, and this central portion is nucleus. Okay, so when you talk about system of atoms, okay, so system of atoms can be like this. So this is an atom, this is another atom, this is one more atom, and this is one more atom. Alright, what is this? This is a system of atoms, group of atoms. So this is isolated atom, but usually when you take a sample of a matter, it will be in this format, isn't it? It will be in this format. Now inside this atom, it will have its own nucleus, own electrons, its own system. This will have its own nucleus, own set of electrons. As per Bohr's postulate, they will be rotating in a particular orbit. Similarly, the case with this, it will have its own nucleus and the orbits. So this is the meaning of that term, system of atoms, group of atoms. Now basically what happens when you take isolated atom, this is there is not much to study about. There is an atom, inside atom there is a nucleus, around it atom, this electrons are rotating. All these things we have studied in modern physics. What we are interested in, when there are a group of atoms, how is the interaction happening? Okay, see, any atom, what will be the configuration? There will be a nucleus, there will be orbits, specific orbits, isn't it? These are all orbits, and each orbit has a particular energy level as per Bohr's postulate. When the electron is rotating in a particular orbit, it will have a constant angular momentum. So this corresponds to n is equal to 1, n is equal to 2, n is equal to 3, so on and so forth. Any atomic structure will be like this only. So in the first orbit, you can have 2 electrons. In the second orbit, you can have 8 electrons. Okay. In the third, 18 electrons. How you are getting it? It is 2n square, right? In the first, 2 into 1 square. In the second, 2 into 2 square. In the third, 2 into 3 square, 18. So on and so forth. Now, you can have atoms where, if you take sodium, let us say, sodium atomic number is 11. Okay, so what will be the arrangement? Can I write this as breakdown into 2 plus 8 plus 1? Can I write it like this? So you can see that in the first orbit there are 2 electrons. In the second orbit there are 8 electrons. So there is only 1 electron in the third orbit. Okay, there is only 1 electron in the third orbit. So atomic arrangement of the sodium is like this. It is nature. Okay, now this electron in the outermost orbit, okay, they are called valence electrons. Okay, you give, because there is only one here. See, suppose in the third orbit, how many should be? You have, in first orbit you should have 2, second orbit you should have 8, and third orbit how much? 18. Am I right? 2n square, right? Now, because only one electron is there, now this will try to move out. Okay. Now suppose it moves out, it comes out of this atomic structure. Now it becomes a free electron. It becomes a free electron. How does it go out? You have to provide energy. You have to provide energy to this. This energy can be provided as heat. Okay, you can give energy as heat. You can apply strong potential difference. Strong potential difference you create. You have seen this battery, charged plates, all this we have seen, no? You create a strong potential difference. There is a creation of electric field in between. So electron will be moved. Okay. So understood the terms valence electrons and free electrons. So every atomic structure we have to study, and we have to see. Suppose there is a particular what you call some particular element. It has got 10. Atomic number is 10. Let us say. So it is 2 plus 8. So it's perfectly stable. But this is slightly unstable. Some energy is provided, it will come out. Okay. So, and when we talk about solids, they can be classified under another category called conductors, insulators, and semiconductors. This is a special type. Conductors, you can call them as metal. All this arrangement is there in the periodic table depending upon their atomic structure. Some behave like conductors, okay, and they always conduct electricity. They always conduct electricity, okay. So conductivity, you have this conductivity coefficient, you have a resistivity, okay. This is the resistivity quotient, this is the conductivity. We know the interrelationship between these two. How much a metal can conduct is told by the conductivity, its conductivity. How much it can resist is told by resistivity. You take any material, you can talk about its how good it is in resistance, means it is told by resistivity, okay. The relationship is their conductivity is 1 upon resistivity. More resistivity, less conductivity, okay. More resistivity means it is opposing the flow of free electrons. It is insulator. This is measured in ohms per meter, and this is measured in Siemens per meter. Their units, okay. So conductors freely conduct electricity, so their conductivity value will be very high and resistivity will be very low. They don't resist, right? Insulators, conductivity will be very low, resistivity will be very high. So they are fixed patterns. The special case is this: they sometimes conduct very well, they sometimes resist very well, okay. This is via medium. All right. So when you talk about resistivity values here, their values here, they vary from 10 power minus 2 to 10 power minus 8, okay. So because this value is 1 upon this, it will vary from 10 power 2 to 10 power 8. This value I am talking about. So resistivity is very, very low, okay. In the case of insulators, resistivity has to be very, very high. It is in the order of 10 to the power 11 to 10. This camera got stuck, I think. Yeah, some problem with the camera, okay. So I was telling that this conductors resistivity value is very, very low, and for insulators resistivity is very, very high, okay. Semiconductors, they vary from 10 to the power of minus 5 to 10 to the power of plus 6. I'm talking about the resistivity values, okay. What is the unit? Ohms per meter. So these are different behaviors that we normally observe. Semiconductors, naturally, they again come under simple types or natural semiconductors, or and compound types. These are man-made. These are available in nature. They are silicon and germanium. Silicon and germanium are the semiconductors that are available as per our periodic table. Silicon atomic number is 14 and germanium it is 32. So what is the atomic structure of silicon? You will have a nucleus, you will have 2 electrons here. Can you write this 14 as 2 plus 8 plus 2 plus 8 is 10 plus 4. So in the second orbit it will have all 8, right? And in the last orbit it will have 4 free electrons, 4 valence electrons. If you provide energy to them, they will become free electrons. Similarly, the case with germanium, Gentlemen, how you can write 2 plus 8, then you can write 18 plus 4. So this is first orbit, second orbit, third orbit, total houseful. So in the fourth orbit, it is only 4 are available. You can write 4s2 4p2, right? 4s2 4p2. In the p, you need to have 6 more. Okay, now p has got 6, you have 2, it needs 4 more. Similar type of arrangement. Okay. So this is another type of classification. So why some behave like conductors, why some behave like insulators, and why some behave like semiconductors? So there is a concept called band theory. We are going to discuss about that. We are going to discuss about that. See, suppose you take a person. He is in a street. He is in a street. This our person is standing alone in the street. Whatever his energy levels are there, whatever his feelings, emotions, desires, expectations with life and all that, his opinions, it will be his own, isn't it? Suppose in the street there are some friends nearby him. Some friends nearby him. What will happen? They will talk to him. They will talk to this fellow. They will give their opinions, they will give their theory, they will give their philosophy. So this fellow will be influenced. Originally, when he was alone, there was no influence. But when this group of people were surrounding this person, they started influencing him. It is natural. So, if this fellow originally has some energy, let us say, his energy levels now will either go up or go down. Let us say this fellow energy level is some X units. Okay. Now, because of all these people, if all these people are negative people, his energy levels will go down. If all are positive people, his energy levels will go up. He doesn't have to do anything for that. He doesn't have to do anything for that. Same is the case with atoms. So here what is happening? These people are influencing them. So in the language of physics, you call this as interaction energies. Interaction energies. They are interacting, no? So they are interaction energies. So we are talking about band. So let us now try to understand one thing. So you replace this person with an atom. So well, you suppose there is an atom. This isolated atom, he just minds his own business. But you arrange atoms nearby, so they will start influencing this, no? Why they will start influencing? Suppose this atom is there. Okay, so this is the nucleus. Let us say in the outermost shell there is a single electron. Single electron is there. You have placed another atom. So in the outermost shell there is another single electron. See, initially when it was isolated, no issue. But this is close to this atom. So this distance also matters. Okay. Now this is nucleus, totally positive charge. This is negative charge. This is negative charge. This is positive charge. So this positive will be attracting this electron. This nucleus will be attracting this electron. So there is a play, no? There is a complex interplay happening. So that is why these interaction energies have come. Okay. So there is an interaction when there are group of atoms together. You take a silicon, you take a germanium, you take a sample. The sample is not made up of one atom. The sample is made up of millions of atoms. So they will be interacting with each other. So now you understood why they are interacting with each other? Because of this concept. Nucleus, electron of the neighbor. Electron of this nucleus and corresponding neighbor nucleus. Positive, negative. So here electron to electron there is repulsion. But here positive, negative attraction is there. There is repulsion, there is attraction. So there is a complex play which is happening. So in this situation there are three terms which is called valence band. Band means nothing, it is just a range. You call it band, you call it range, whatever it is. Valence band, there is a conduction band. You need to understand these terms. And there is a, the third one is forbidden energy gap. We need to understand these three terms. So let us say we have taken a sample. We have taken a sample. Obviously the sample will not have single electron. It will have group of electrons. Okay. Inside the electrons you will have a nucleus, and let us say I am drawing only the outermost orbit. This is nucleus, outermost orbit. Nucleus, outermost orbit. Alright. So in the outermost orbit, let us say one electron is there. Okay. So there will be interaction. There will be interaction. So this is a sample, some sample I have taken, in which there are some system of atoms are there and they are interacting with each other. Why they are interacting with each other, just now we have discussed. You try to plot a graph between energy, okay, and you can say the distance between them, or you take a parameter, okay. So this interaction will be dependent upon the distance between them. Alright. Now this energy interaction all will be in terms of electron volts. Usually the range is 0 to 8 electron volts only. Okay. Or 4 to, it is in the range of 0 to 8 electron volts only. This interaction and all these things are happening now. Now let us say you took all the valence electrons. I told in the just now what is a valence electron, what is a free electron. Valence electrons are the electrons which are there in the outermost orbit. If the atom is completely stable, you will have perfect arrangement. First orbit will have 2 electrons, second orbit will have 8 electrons, third orbit will have 18 electrons, so on and so forth. But for some cases, like I told you, sodium, so you have only 1 electron in the outermost shell. Alright. Now what happens is, you take, this is atom 1, atom 2, atom 3, atom 4. Okay. Now you pick up all these valence electrons and you plot their energy levels. You calculate their energy levels. Okay. And you got some different range. You got the values, you got some values. So this is, let us say, 0, this is -4, this is -8, this is -12, this is +4, this is +8, this is +1, so on and so forth. You kind of plotted their energy levels. Okay, this is a particular atom, so they will have a band, let us say from 7.9 to 8.7. It is varying in between, so you plotted that. You just draw a line there. Now this is called a band, which is valence band. Band means range. What is this? This is a range. We are just graphically showing them. So this is our valence band. Alright. Now here there can be some free electrons also. Alright. How that free electron has come? Right, let us not discuss about that right now. Let us say some free electrons are there. Okay. So and you plotted their energies also. How much energies they are processing. Okay. They are having some values, 0.2, 0.4, 1.2, something like that. Let us say they are varying between 0.4 to 1.2. This is also a band. It is conduction band. Okay. So it will have a range. It will have a range. It is our conduction band. This is our valence band. Understood the difference between what is a conduction band, what is valence band? Why it is called a conduction band? Because they are conducting electricity. No? What is electricity? Is movement of electrons. You have given some energy. There is a, see, you have group of atoms like this. Okay, and you have some valence electron like this. You gave some energy to this. It became free. It knocked out the electron in the neighbor one. It knocked out the electron in the neighbor one. What is happening? The electron is moving, no? So it is conduction of electricity only. It's a good conductor, right? Anyway, so you gave some energy to the valence and it became a free. So all these free electrons, they came into some certain range. So that is called a conduction band. You can see here that there is a conduction band, there is a valence band. In between, there is null space. In between, nothing is there. This is your forbidden energy gap. Energy gap. Why? The electron can be here or here, not in between. Bohr's law, Bohr's postulates. Electrons can rotate in a particular orbit we have studied. Okay, either in the first orbit or the second orbit or the third orbit. It cannot rotate somewhere in middle. So this is the nucleus as per Bohr. That is, this is nucleus. Electron can be here or here. N is equal to 1 or N is equal to 2. It cannot be here, no, somewhere in middle. Okay, so it corresponding to that, we can talk in terms of energy also. So conduction band has a particular energy levels. Valence band has got some particular energy range. In between the gap is there, that is called a forbidden energy gap. Suppose this gap is very large. That means you need a large amount of energy from valence band to conduction band. You need a large amount of energy, right? Insulators, that is the case. Very large, they behave like insulators. Understood? Why they behave like insulators? Because in insulators, from the valence band to conduction band, you have to provide energy, and that energy is very large. So that is why they behave like insulators. Suppose this gap is medium. Suppose this is my conduction band and this is my valence band. This gap is less than this gap. Let me draw this line over here. Okay. This gap is less gap. Comparatively, this quite less. They behave like semiconductors. They behave like semiconductors. When the gap is less, when the forbidden energy gap is less, reasonable, it behaves like a semiconductor. Okay. Then what happens in the case of conductors? So if I try to draw over here, in conduction band, what happens is, see, this bottom one is your valence band and this upper one is the conduction band. And you can see there is a region of overlap. There is an overlap. There is an overlap. So this is the case of conductors. This is the case of conductors. Okay. In conductors, what happens? There is a overlap of conduction band and valence band. So this happens in conductors. Insulators, the gap is very big. Semiconductors, the gap is very less. Now what does this mean? It means that if you provide some energy in the valence electrons, they will move to become free electrons. Okay, they will move to become free electrons. So suppose you have a atomic, some structure is there, some free electron, this is a valence electron. I gave some energy and it became free. So here it was in which range? It was in valence band range. Here it is in conduction band range. So this energy gap is less. Okay, so they behave like semiconductors. Sometimes they behave like conductors. So how do you do that? You heat it, or you put it in the electric field. This electron will be knocked out easily. Most of all these electronic equipments, what you're seeing, they're made up of semiconductors only. Okay, whereas in case of insulators, you have to provide a very large amount of energy. When plastic is there, you have to provide a large amount of energy. Even then also you will not get free electrons. Okay, you want to make a heater, an electric heater. Will you make that with a rubber, plastic, or you will make with some iron? Iron is a good conductor. Okay, so that decides which material we have to choose for which purpose. Okay, so so this is the thing. Okay, so here in conductors, what happens is, you don't have to provide any energy to make valence electron into free electron. See, valence electron is there. In conductors, what happens? You have valence electrons. You are trying to make them free electrons. Okay, this is what you are trying to do. So special energy you don't have to give for conductors. Sometimes they behave like valence electron and sometimes they behave like free electrons. So that is the property of conductors. But in the case of semiconductors, you have to give some energy. Then they start getting these free electrons, they conduct electricity. Some energy has to be given to them. Okay. And in the case of insulators, no matter how much energy, very large amount of energy you give, even then you don't get free electrons or very few electrons, which is of no use. Okay. So this is what is band theory is all about. It is interaction between the atoms. You taken a sample. This sample can be silicon. This sample can be germanium. This sample can be sodium. Sample can be chlorine. So you can plot the graph like this. So depending upon these values, we can say whether the element is able to conduct or is not able to conduct, or is it a special case of semiconductors. The semiconductors, in the case of silicon, I told you, in the outermost shell you have got 4 electrons. Okay, outermost shell you have got 4 electrons. Okay, so what happens? You provide energy, those 4 electrons will move. Those 4 electrons will freely move. Unless otherwise you provide that energy, they won't move. When you provide energy, they will move and they will conduct. So that's why it's a semiconductor. What I'm saying here, in the case of, I'm just removing this, why you are calling silicon as a semiconductor? So normally it won't conduct. Okay, what was the arrangement? This was the arrangement. Okay, here there are 2, here there are 8, right? And here there are only 4. These 4 valence electrons, if provided energy, they will move, they will conduct only when you provide energy. So that's why they behave like semiconductors. By themselves they won't conduct electricity. Only when you provide energy they will behave like conductors. That's why they are semiconductors. We see some more concepts in the next class. See you. Bye bye.